This is the first year algebra-based physics course. Topic 2, one-dimensional kinematics. This section, 2.12, is about free fall. I'll be discussing what a gravitational force is and how the acceleration, velocity, and displacement of an object change or don't change during free fall. Some vocabulary before we get started. The gravitational force. Now, a synonym for gravitational force is just the word gravity. So gravity is a force. Keep that in mind. The symbol is Fg, gravitational force. Now, all masses attract each other. All right, so for example, this cantaloupe and this apple, if I put them in outer space, over thousands of millions of years, they're going to get closer and closer and closer together. All right? All masses attract each other. The force, the pull, in this case, this is an attractive force, so they're pulling themselves together. All right? The force that one object exerts on another due to the mutual attraction between their masses is called a gravitational force. All right? So they're pulling on each other. All right? And this is called the gravitational force. Now, acceleration due to gravity, also called free fall acceleration. The symbol is a lowercase g. Right? Now, don't ever call this gravity. It's wrong. All right? If you mean acceleration due to gravity, say acceleration due to gravity. All right? So acceleration due to gravity is the rate at which any object accelerates toward the center of a celestial body. We're going to use this specific definition. I mean, obviously, the apple and the cantaloupe in outer space accelerate towards each other, but we're going to reserve this definition of acceleration due to gravity for the way we're going to use the term in the first year physics class. And that's pretty much exclusively for when objects are dropped on the surface of a celestial body. Celestial body could be a planet, a star, a comet, an asteroid, all right, a moon, all right. You're standing on the celestial body, all right. Let's say I'm standing on the moon, all right, and I let these go, and they accelerate. In other words, they drop faster and faster toward the center of the moon. Now, of course, they're going to stop when they hit the rocky surface of the moon, all right, or the dusty surface of the moon. But and again, this is going to happen on Mars, on Venus. All right, a little different because you can't stand on Jupiter. Jupiter is a gas giant. All right, but again, we're going to talk specifically for acceleration due to gravity about how when you are on some celestial body, for most cases, we're going to be standing on Earth. All right, and if you drop an object, all right, it accelerates. It goes faster and faster toward the center of the Earth, which we're going to call down. And you can see that I have some protective pillows on the floor. I'm not going to let the cantaloupe and the apple get damaged or broken. I'm going to eat them later. No wasting food. Our last vocabulary word, actually phrase, is the phrase free fall. An object is said to be in free fall when the only force acting on the object is a gravitational force. Gravitational force is also commonly called gravity, or it's the object's weight, and the symbol is Fg. Now, let's take a football, for example, and it doesn't matter whether you're playing football on the Earth, right? Maybe you're with the Patriots, or you're playing football on the moon. Maybe you're with the Lunar Lions team. In any case, you can throw the football straight up in the air, although we don't know why a football player would do that, but you can throw the football straight up in the air, or you can pass the football in an arc, right, to the quarterback of the Lions, all right? And once the ball has left the passer's hand, the only force, as the ball is flying through the air, or lack of air on the moon, the only force on the ball is the pull of the Earth downward, the gravitational force that the Earth or the moon or Halley's Comet, wherever it is you're playing football, is exerting downward toward the center of the Earth or the Moon on the object. Right? So it doesn't matter, again, if you toss the football straight up, catch it, or pass it across to your quarterback, the football is in free fall because once it leaves the passer's hand, the only force acting on it is the gravitational force. The planet, the moon, the comet pulling the object down toward the center of the celestial body. Rah! Go, Lunar Lions! All masses attract each other. So on the Earth, if you have a table and two boxes, let's just focus on the two boxes. We're going to kind of ignore the table for a moment. Those two boxes, by virtue of the fact that they both are made out of matter and they both have mass, are attracting each other. Right? This box number 2, is pulling box number 1 to the right, and box number 1 is pulling box number 2 to the left. So how come we don't see the boxes get closer and closer? Well, you got a couple things. First of all, you got air between them. The air gets in the way. All right, second of all, and more importantly, you've got friction here. There's friction between the box and the table. So if the boxes were to try to go towards each other, they can't, because the friction between the box and the table is stronger than the force of gravity, the gravitational force, pulling the two boxes together. Now, if you take those two boxes or two apples or two anything and put them in outer space, they are not, there's no air to get in the way, there's no friction to get in the way. So after thousands of years or millions of years, right, with the gravitational force of this apple pulling that apple, and this apple pulling that apple, all right, after thousands of years, millions of years, whatever, okay, those two apples are going to come together. All right, they can do it in outer space because all this other stuff is not getting in the way. Now, come to what we want to talk about today. All right, here's the Earth. Here's a box. The Earth is attracting the box down. The box is attracting the Earth up. All right, but since the box is so small, it's going to move faster. All right, the Earth is not going to move up very much. The box is going to move down faster. So we say that the box is falling. And while we're at it, for many, many problems in physics, we're going to ignore the air resistance, because the air resistance is so much weaker than the force of gravity, the gravitational force pulling the box down. All right, so in this case, we don't have to worry about the air resistance. We're only going to look at the gravitational force on the box. And this box will free fall down until it hits the surface of the Earth. A push or a pull in physics is called a force. And the mutual attractions of two masses toward each other are called gravitational forces, symbolized gravitational force, capital F, and the subscript lowercase g. So this time, let's hold a box out of the window of a tall building. And of course, here's the Earth. Now, we know that the Earth pulls the box down, and we know that the box pulls the Earth up. Right? Two masses, and they're attracting each other. Now, we know that the box is going to fall faster and faster to the ground. The box is going to accelerate. We can see the box accelerate. But what we have to realize is that the Earth is also going to be pulled upwards toward the box. Now, which one do you think is going to accelerate faster? Right, is the little box going to accelerate faster? Woo! Or is the Earth going to accelerate faster toward the box? Somehow, I don't see the Earth accelerating very quickly upwards toward the box. What's happening is that the box is so small, it's affected more. It accelerates faster. The Earth is so large that its acceleration upwards is imperceptible. We might as well just ignore it completely. All right, so what's happening is that the box is accelerating down towards the Earth. Now, you see, or you can see millions of different objects accelerating towards the Earth every day. You see things falling, you see mountain slides, rocks falling off of mountains, you see raindrops, you see snowflakes coming down. All these objects are accelerating toward the center of the Earth. If an airplane were to run out of fuel, the airplane would accelerate toward the center of the Earth. All right, so all of these objects are experiencing an acceleration. And the amount of that acceleration, right, we're going to call it g. It's a form of acceleration a, right, and it's going to be exactly 9.81 meters per second squared. We're going to round that off for all intents and purposes to 10 meters per second squared to make all of our calculations a lot easier. Right? So all of these objects have an A, sometimes symbolized G. They're all accelerating toward the surface of the Earth. So how fast do objects accelerate towards the Earth? Right? What is the rate of acceleration for objects that are falling? Now, the first thing I'd like you to do is take a look at the front page of the physics reference tables. Let me take you there right now. So why are we calling g a constant? In other words, how high up is g still going to be 9.81 on the Earth? Here we have a picture of the Earth and a box on the surface of the Earth. The radius of the Earth, or the distance between the box and the center of the Earth, right, is 6.37 times 10 to the 6th meters. You can find that information, again, on the front page of your reference tables. The average or mean radius of the Earth. Now, what we can do here is calculate at what radius the g, little g, for the Earth is 9.81. So we've got here an equation. Now, we already know that the radius is 6.37 times 10 to the 6th. But we're just going to double check, and then we're going to try to figure out how high up we can go, and it's still 9.81. All right, now, the equation is that the radius is going to be equal to big G, which is another constant on the front of the reference tables. M1 would be the mass of the Earth, all right, and little g, of course, is the acceleration due to gravity for the Earth. So we plug in from the front of the reference tables big G, the mass of the Earth, and little g. All right, and if you do all this math, multiply 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th, multiply those, hit equals, divide by 9.81, hit equals again. Now take the square root of all that. You're going to get 6.376 times 10 to the 6th. Right, to three significant figures, 1, 2, 3, this is what we find on the front of the reference table, 6.37 times 10 to the 6th meters. Now, the question we want to ask is when this, for example, changes to 9.80. So, let's plug in here, right, R equals, now the big G does not change. It's a universal gravitational constant, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. The mass of the Earth does not change. 5.98 times 10 to the 24th kilograms. And again, you're finding big G and the mass of the Earth on the front page of your reference tables. Now what we are changing is we want to know what the distance is when G goes down to 9.80 meters per second squared. All right, so what we do is we plug in these numbers. All right, 6.67 second E negative 11 times 5.98 second 24, hit equals, divide that by 9.8, hit equals, now take the square root, and we're getting that R, all right, for it to be 9.8, R would have to be 6.379 times 10 to the 6th meters. All right, so in other words, the box, all right, from the center here, I'll make this blue, all right, the box from the center, all right, this would have to be 6.379 times 10 to the 6th. All right, now down here, we actually calculated 6.376. We got one more significant figure, all right, than we had before. So let's put that in there. 6.376. And this is all a very, very rough estimate. But it'll just give us an idea, all right, about how high you would have to go for this to actually change to 9.80. All right, so what we're going to do now is figure out the height above the surface of the Earth. All right, we know that here to here, and this is not drawn to scale, obviously. We know that from here to here, we've got 6.376. We know that from here to here, we've got 6.379. If I want to know the height above the surface of the Earth, all right, from here to here, we're going to have to subtract these two distances. All right, so let's do that. All right, 6.379 minus 6.376 to the 6th power, and we're getting 3,703 meters. All right, so 3,703 meters above the surface of the Earth. All right, so let's erase this. All right, so how high up, all right, before it changes to 9.80? All right, 3,703 meters up. All right, 3,703 meters right there. Okay, now let's put that into a perspective. All right, I'm going to change it to kilometers. All right, 1,000 meters is 1 kilometer. All right, and then I'm going to change that to miles. How many miles up can we go before this drops down to 9.80? All right. Now, we know that 1.6 kilometers is 1 mile. All right, so let's do the math. We've got 3,703 divided by 1,000, and then divided by 1.6, 2.3 miles. All right, 2.3 miles up above the surface of the Earth. So let's just say you can go about 2 miles up into the sky, and the acceleration due to gravity of the Earth is still 9.81. Okay, right about that point is where it's going to start changing to 9.80, approximately. All right, rough approximation. All right, but that's why we call this a constant, because for most of what we do, all right, throwing a football around, or even some helicopters, or everything we do down here, you know, below 2 miles up, the acceleration due to gravity for the Earth is 9.81. All right, so that's why it's a constant. The next question that we need to explore is this one. Basically, this is all the same question. Does the mass of an object affect how fast it falls? And the answer is no. In other words, let me ask this another way, because I'm not so sure that I like that answer. Do more massive, and that would mean heavier objects, fall faster than less massive, and that would mean lighter objects? Do more massive objects fall faster than less massive objects? And the answer is no. But wait, hold it. Let me ask this a different way. If we drop a marble and a bowling ball from the same height at the same time, which one hits the ground first? And the answer is neither. They hit the ground at the same time. They hit the ground at the same time. This is something you really want to get straight. A small object and a large object, assuming the small object is lighter and the large object is heavier. The heavier object does not hit the ground first. The two objects hit the ground at the same time. Now, all of this assumes that we can completely neglect air resistance. In other words, it's not a piece of paper floating down like this. That would be affected by air resistance. The air resistance would tend to keep the paper up in the air. Right? If you take two objects and there is no air resistance, now you can actually watch these videos on YouTube. Type in keywords hammer, feather, moon. All right, and you will see that on the moon, if you drop a feather and a hammer at the same time, they hit the ground together. There are also experiments in vacuum chambers that scientists at NASA have done. If you take all the air out of a large building, now obviously there's nobody standing in the building, but you take all the air out of a large building and you electronically allow a feather and a hammer to drop at the same time, or a feather and a bowling ball, whatever. As long as there's no air resistance, the heavy object and the light object, right, are going to hit at the same time. All right, so the mass of the object is not going to matter during these calculations. All right, that's why these calculations with different objects, marbles, bowling balls, a car flies off a cliff, these calculations are not, we're not going to see M for mass in these calculations. That's why these calculations are falling under the kinematics topic. We don't have to worry about M for mass. When we start worrying about M for mass, we will be in topic 4, the forces topic. All right, so no mass, don't worry about the mass when you do these calculations. So, just to make sure that the two objects hit the ground at the same time, let's drop a marble and a bowling ball. Let's drop two objects, a marble and a bowling ball, together from the same height. All right, and see what each acceleration, velocity, and displacement are after 1 second, after 2 seconds, after 3 seconds, after 4 seconds. So we're going to drop the marble and the bowling ball from a height of 80 meters. Okay? So here we go. Now, first of all, we know that the acceleration due to gravity of the Earth is constant for every object. It doesn't matter whether it's little, big, a mouse, an elephant. The acceleration is the same. It does not change. All right, until you get 2 miles up, 10 miles up, whatever, and we're not going up that high. So for all intents and purposes, the 9.81 meters per second square, we're going to round it off to 10, does not change. All right, so after 1 second, what's the acceleration of the marble and the bowling ball? After 1 second, it's still 10. All right, now actually, I apologize. Let's take a look at the 0 mark first. At 0, the time is 0, the displacement is 0, the velocity is 0. I'm holding them both. They're not moving. The velocity is 0, but the acceleration is still 10. In other words, the Earth, even though I'm holding the marble and the bowling ball, the Earth is still pulling on them. So they are still experiencing an acceleration of 10, even when I'm holding them, waiting to let them go. The acceleration due to gravity, little g, is constant. So now all the way down, the acceleration is constant. All right, after 2 seconds, the acceleration is still 10 meters per second squared. See the unit, meters per second squared. After 3 seconds, the acceleration is still 10 meters per second squared. And after 4 seconds of falling in free fall, the acceleration is still 10 meters per second squared. All right? Now remember, we are talking about free fall, and what we mean is that the only force on these objects as they're falling is the Earth pulling them down. In other words, the weight of the marble pulling itself down, being pulled by the Earth, right, and the weight of the bowling ball going down, being pulled down by the Earth. I mean, if you like, we could draw, all right, the force the Earth pulls the marble down and the force the Earth pulls the bowling ball down. All right? All right, now, let's draw the marble and the bowling ball at the 1 second mark. After 1 second of falling, where are they and how fast are they going? Okay, so I'm going to put the marble down here now. All right, here's the marble. All right, and here's the bowling ball. The bowling ball is down to here also. Now remember, they fall together. All right, now, first of all, how fast are they both going after falling for 1 second? All right, now remember also, it doesn't matter what object we drop. After falling for 1 second, all these are going to be the same. Whatever we put here, whatever we put here, whatever we put here are the same no matter what you drop, because the mass doesn't matter. All right, so now let's see what the speed is after falling for 1 second. Well, what does an acceleration of 10 meters per second squared mean? All right, if the acceleration, now this is the acceleration due to gravity g, it's a type of acceleration, right? It's 10 meters per second squared. Now, I'm not going to worry about the fact that everything here is negative. The acceleration is falling down, all right? So that's negative. The velocity is, they're going down, so all those are negative. And the displacements, if I put 0 up here, then everything down there is negative. I'm not going to worry about the negatives, right? It's not important to worry about the negatives. All right, now, 10 meters per second squared means 10 meters per second per second. It means that the velocity changes 10 meters per second every second. So after 1 second, if it started at 0 and it's supposed to change by 10 meters per second, that means that now the velocity is 10 meters per second. All right, and I will tell you that it has fallen exactly 5 meters down. I'll show you a little later how to get these calculations for displacement. Now, after 2 seconds, the acceleration is still constant. The acceleration is 10 meters per second squared. How much is the velocity? How fast are the marble and the bowling ball falling? Now we know that when things fall, they go faster and faster. So we know that the velocity is more than 10. Well, what does an acceleration of 10 meters per second squared mean? It means 10 meters per second. Every second that goes by, the velocity increases by 10. What was the velocity at 1 second? It was 10. What's the velocity 1 second later? From 1 to 2? It's 10 more. So now the velocity is 20 meters per second. How far down is it? It's down at exactly 20 meters. And again, well, we've got the meters up there. Okay. And again, I will show you in just a few minutes how to calculate the displacement as the objects fall down. All right, so where is the marble now? The marble is here. All right, the bowling ball is in the same place, or I should say at the same height. All right, there's the bowling ball. All right, and now we ask ourselves, after 3 seconds of falling, right, what's the acceleration? We know. What's the velocity? And what's the displacement? Let's figure it out. We know the acceleration is constant. The acceleration is still 10 meters per second squared. All right, what does an acceleration of 10 meters per second squared means? It means that every second that goes by, the velocity changes by 10. So what's the velocity after another second has gone by from 2 to 3? Add another 10. The velocity of each object is now 30 meters per second. And I will tell you that they have fallen 45 meters down. Now, I also want you to notice something here. Notice that in the first second, both objects fell 5 meters. All right, so they both fell 5 meters. In the next second, from 1 to 2, they fell from 5 to 20. They're going faster, so they fell further. They fell 15 meters in that next second. What about in the next second, from 2 to 3? How far did they fall during this interval? Well, they fell from 20 down to 45. So how far did they fall? They fell 25 meters in that time. Why are they falling more and more distance in each same amount of time, in 1 second, in 1 second, in 1 second? Because they're going faster and faster. So they're covering more distance in the same 1 second of time. All right. Let's put our marble here. Let's put our bowling ball here. All right, here's the bowling ball. All right, now remember, they're falling together as all objects are going to do that are released from the same height at the same time on Earth. The Earth, by the way, is pulling them down the whole time. The Earth is pulling the marble down, pulling the bowling ball down, pulling the marble down, pulling the bowling ball down, pulling the marble down, pulling the bowling ball down. Now you also notice that the force that the Earth exerts on the marble is smaller than the force the Earth exerts on the bowling ball. That force is the weight of each object. And obviously the bowling ball weighs more than the marble, but it doesn't matter. They fall at the same rate. All right, now the last place where they end up would be down here. We're going to stop at 4 seconds. Now you see, after 4 seconds, all right, first of all, at the 3-second mark here, it's going much, much faster. So it's going to fall a much greater distance in 1 second. All right, it's going to fall from 45 down to 80 in 1 second. Now, I happen to know these numbers, and I will show you how to calculate them. So that means in this last second here, it fell, let's see, 45 to 80. All right, we've got 35. All right, 35 meters is what it fell in this second from here to here. So you see this displacement interval getting bigger and bigger as it falls faster and faster. The acceleration has not changed. It's still accelerating at a rate of 10 meters per second every second. So if at 3 seconds its speed was 30, 1 second later its speed has increased by 10, right? By 10 per second. So now the speed is up to 40 meters per second. And since we dropped it from a height of 80 meters to begin with, the ball, all right, the marble, all right, and the ball hit the ground. And we better hope there's nobody down there, because even if you get hit with a marble from that, forget the bowling ball, you get hit with a marble from that height, that's going to hurt. Okay? So there we are. All right. So we see when an object is in free fall, right, when the only force on the object is the force of gravity, the Earth pulling the object down, we see that the acceleration does not change. The acceleration is constant. The velocity, it gets faster and faster as it's going down. The displacement gets larger and larger, but also the interval between the same 1 second of time also gets larger and larger. And we see the time going by, 1 second, 2 seconds, 3 seconds, 4 seconds. All right, so you see the patterns. The velocity is going up by the same amount, 10 to 20 to 30 to 40. The amount that the displacement increases each second increases. See, the velocity went up by 10, went up by 10, went up by 10. But the displacement, right, the displacement went up by, from 0, went up by 5. Then 1 second later, it was 15 meters further. Then 1 second later, it was 25 meters further. And then 1 second later, it was 35 meters further. I should also mention that these lines here are representing the displacement. All right, we don't need lines for the velocity and the acceleration. Those numbers are not being graphed. We're just saying what they are at this time. What they are at this time. What they are at this time. These lines here as a graph are showing you the change in displacement. Okay? So, free fall. Let's look at it in another way. The magic chart is a way to have some common sense, some physics common sense, about how far objects fall, what their speeds are, and how fast that happens. Now, the rules for using the magic chart are really important. So let's take a look at the rules. First of all, the way we're going to put the numbers on the chart today, these numbers are for the Earth only. In other words, where g, or the acceleration due to gravity, is 10 meters per second squared. 9.81, but we're going to say 10 meters per second squared. So these numbers would not be correct for the moon, or for Jupiter, All right, these numbers are going to be for Earth only. But 80 to 90%, no, higher, 95% of the problems that you do in physics are going to be for objects on the Earth. All right, so these numbers are for Earth only. Now, we can adapt the numbers for other celestial bodies in a later lesson video. Second rule, the object must start from rest. The velocity at time 0 is 0. The object must start from rest. And obviously, the object starts with no displacement. All right, so everything starts at 0. All right, now, how did I calculate the velocities and the displacements in the previous section? Remember when we were doing the marble and the bowling ball? How did I do those calculations? Well, first of all, the time is very simple. The time is going to be 0 seconds, 1 second later, 2 seconds later, 3 seconds later, 4 seconds later. Let's go down to about 6 seconds later. All right, let's memorize down to about 6 seconds. All right. Now, you've got an equation on your reference tables. It's on the mechanics page, the displacement equation. All right, here it is. We can use this equation to figure out how far down an object falls when it's dropped from rest on or near the surface of the Earth, how far down it falls each second. Now, the initial velocity, since it starts from rest, the initial velocity is 0. All right, so the displacement, how far down it goes, is going to be 1/2 AT squared. Now, we know that A is 10. All right, 10 meters per second squared. All right, and the time is going to have to be squared. So really, what this boils down to is that the displacement is going to be 1/2 of 10. That's 5t squared. All right, so the displacement is going to be 5t squared. All right? Okay. I think we'll do the equations first, then we'll fill in all the numbers. Now, how fast, what's V final? How fast is the object going after 1 second, after 2 seconds, after 3 seconds, after 4 seconds, etc.? The initial velocity, starting from rest, the initial velocity is 0. So V final is going to be the acceleration due to gravity, right? G, 10 meters per second squared, times the time. So it's going to be 10t. V final is going to be, all right, 10t. All right, so now watch how simple this is. After 1 second, when the time is 1, how far down has the object fallen? Remember, we take an object. Let me grab my, my apple again. All right, we take an object, okay, and we drop it from rest, okay? After 1 second of falling, how far has it gotten? How far down is it? 1, t is 1, 1 squared is 1, times 5 is 5. How fast is it going after 1 second? 10 times 1, it's going at a speed of 10 meters per second. After 2 seconds, 2, the time is 2, squared is 4, times 5 is 20. After 2 seconds, it has fallen 20 meters. And remember, we don't care what the object is. It can be a marble, it can be a bowling ball, a mouse, an elephant, a car driving off a cliff. All right? It can be firing a bow and arrow. Right? How far down does the arrow go? If I fire that arrow from the top of a cliff, how far down does it go in 2 seconds? It's gone down 20 meters. Right? I don't know how far down the bottom of the cliff is, down there, but so far it's gone down 20 meters. What's the speed, the down speed? All right, after 2 seconds, 10 times 2 is 20 meters per second. That's a coincidence there that those both happen to come out to 20 all the time. All right, now, after 3 seconds, how far down is the object? 3 squared is 9, times 5 is 45 meters down. How fast is it going down? What's the speed now? 10 times 3 is 30 meters per second. All right, am I doing a good job of keeping this straight? I hope so. All right, we'll put that there. Okay, I just want to keep my rows straight. Okay, after 4 seconds, 4 squared is 16 times 5, all right, is 80. All right, so after 4 seconds, all objects fall down 80 meters if they're in free fall. All right, and what's the speed of the object? All right, 10 times 4, all right, time t is 4, so that's 10 times 4 is 40 meters per second. All right, after 5 seconds, how far down is the object? What's the displacement? Where is it? 5 seconds squared is 25 times 5. It's 125 meters down. Now, up to this point was where we went in the last little section. We're going a little bit further, no big deal. All right, how fast is it going after 5 seconds? 5 times 10 is 50. It's falling down at 50 meters per second. By the way, what's the acceleration the whole time this is all happening? It's 10 meters per second squared. You want to say 9.8? I mean, we're using 10 here, obviously, for the calculations because the math is a lot easier. You can say 9.81, do the calculation that way. Let's do 10, it's so much easier. The acceleration is 10, 10, 10, 10, 10, 10, 10, 10, 10. The acceleration is a constant. It does not change, as long as we don't go too far into outer space. All right, the acceleration due to gravity for the Earth does not change. And finally, 6. 6 squared is 36, times 5 is 150 plus 30 is 180, okay? So 180 meters down. 10 times a time of 6 is 60 meters per second. All right? So I don't know if you can see down here, but down at the bottom here, at 6 meters, at a time of 6, the d is 180, and the final velocity is 60 meters per second. So what you want to do, seriously, is memorize this chart. You want to memorize this little equation here. You want to know where the equation came from. You want to know that it's the displacement equation, that the initial velocity was 0, and that a was 10, because the object is falling near the surface of the Earth. So the acceleration is the acceleration due to gravity of the Earth, or 10. Half of 10 is 5 t squared. Over here, this equation, right, you want to remember where this equation came from. The initial velocity was 0. The acceleration due to gravity of the Earth is 10, 10t, 10t. All right, so make sure you know where this equation came from, where this equation came from, and then I would just memorize 5, 20, 45, 80, 125, 180. All right, and here I would memorize, again, 0, 0, 10, 20, 30, 40, etc., etc., etc. Okay? And you can see what we saw in the last section also, that the velocity goes up by the same amount each time. This went up by 10, this went up by 10, this went up by 10, up by 10, up by 10. This went up by 5, then from here to here it went up by 15, then from here to here it went up by 25, then from here to here it went up by 35, then from here to here, right, it went up by 45. And we can imagine that from here to here that must have gone up by 55. We see a pattern for sure. All right? So, the magic chart, and I would absolutely memorize the magic chart. Remember, these numbers that you've memorized are only for Earth and for an object that starts from rest. If you take the object, all right, I don't want to hurt my apple here because I'm still going to eat this apple later, but if you take an object and throw it down, wham, right? If I just allow it to go from rest, I just let it go. But if I throw it down, wham, wham, right, then it's not starting from rest. All right, so keep that in mind. All right, now let's do some problems, some free fall problems based upon what we've learned in the video and in the rest of our physics course. Just another word about typical free fall problems. If no other planet is mentioned, it is always assumed that the problem takes place on Earth. So therefore, the acceleration due to gravity, g, is 9.81 or 10 meters per second squared. Another note, for free fall problems, remember the mass of the object falling does not matter. Ignore the mass. Don't use it in the problem. We'll be doing problems where we have to use the mass a little later in the course. Problem number 1. A 2-kilogram rock is dropped from rest from the top of a 125-meter cliff. Calculate the speed of the rock after it has fallen for 3 seconds. Now, the first thing you want to keep in mind is that the 2 kilograms is not important. You're not going to use that number to figure out the speed of the rock. Remember, we did a whole bunch of problems in the previous little sections here. We didn't worry about the mass of the rock at all, and yet we were able to figure out how far it fell, how long it took, and how fast it was going. So forget the mass of the rock. All right, they're just putting that in there to confuse you. All right, we don't need this number. All right, now, the other thing I want to say to you is that for this topic, you should have the magic chart memorized. All right, so you should be able to do this. All right, time, distance, final velocity. All right, 0, 0, 0, 1, 2, 3, 4, 5, 6. All right. After falling for 1 second, I'm down 5 meters. My speed is 10, all right, meters per second. Down to 20, that's 45, that's 30. I know this is 30, 40, 50, 60. And this is 45, 80, 125, and 180. So what you see right away is that for the 125 meters, right, for the 125 meters, it would take 5 seconds for the rock to get down there. All right? So after 3 seconds, all right, the rock is not down to the bottom of the 125 meters. All right? So that means the 125 meters really isn't important either. All right, I want to know the speed of the rock after it has fallen for 3 seconds. Well, after it's fallen for 3 seconds here, all right, after it's fallen for 3 seconds, I know from the magic chart that the speed of the rock is going to be 30 meters per second, and it's fallen down 45 meters, not the full 125. All right, so I already know the answer is 30 meters per second. But if this is a multiple choice question, you're done. Pick the 30 meters per second, and you're done. But if this is a written question, right, then we have to figure out some equations that we can show the work and get the credit. Because if you just put 30 meters per second for a written question, you're going to get no credit. All right, so again, I want you to have the magic chart memorized. You already know that the answer is supposed to be 30 meters per second. All right, now, let's do a written problem. All right, given. All right, we've got the mass of the rock is 2 kilograms. We pretty much know that we're not going to need that. All right, we know that the distance here, right, is 120. Let's say distance total, all right, is 125 meters. We're really not going to need that either. That's not what they're talking about. They want to know what's the speed of the rock after it has fallen for 3 seconds. All right, the time, all right, is 3 seconds. Now, if the rock is dropped from rest, we know that the initial velocity is 0 meters per second. We want to know the speed, right, after. So what we want to know is the final velocity. All right, I want to know the final velocity, and whenever something is falling, it's being acted upon by g, which is a type of acceleration, right, which is 10 meters per second squared. Okay? All right, so we go to the reference tables, we go to the mechanics page, we pick out an equation that has A, V final, V initial, and T. The equation we come up with, V final equals V initial plus AT. Okay? V initial is 0. All right, never plug in zeros. If something is 0, get rid of it as quickly as you possibly can. So V final is going to be A times T. All right, V final. Now, do they want the final? They want the final speed. All right. All right, V final. All right, A is 10 meters per second squared. The time is 3 seconds. The final velocity is 30 meters per second. All right, now, if they ask us for the final speed, we don't care about direction. It's 30 meters per second. If they ask us, all right, so this would be the speed. If they ask us for the final velocity, it's going down, so it would be negative 30. All right, now they did ask us for the speed of the rock, so we don't have to worry about the negative. All right, remember, speed is a scalar. We don't care about the direction. If they ask us for velocity, we have to tell a direction, right, if we know it. All right, otherwise we can't do the velocity. But if they ask us for the velocity, we have to say that it's either down or negative. I'll put negative. All right, but they asked for speed, so I don't need that answer. Here's your answer right here. All right, it's 30.0 meters per second. Okay. This was a very, very simple problem. The only thing that was tricky is you can't use this 125 because at the time of the question, 3 seconds, all right, if this is start time, at 3 seconds, the rock is here, the 125 meters is down there, all right, the rock has only fallen down 45 meters, so this 125 does not apply to a question asking about how far or how fast is it going at the end of 3 seconds. All right, the 125 is down there at 5 seconds. So the 125 is another number put in there to kind of throw you off. All right, next problem. Here we go. Free fall problem number 2. How long will it take a 1 times 10 to the negative 2 kilogram marble dropped from rest from the top of a 125 meter cliff to reach the base of the cliff? Now, the base of a cliff is the bottom of the cliff. If this is a cliff, in other words, this is a mountain, right? So this here is the cliff. Here's the bottom, all right? This is the top of the cliff. This is the base of the cliff right here. The bottom close to the cliff is the base of the cliff. All right, just want you to know what that means. All right, now, again, it's dropped from rest. It's happening on Earth. You can use the magic chart. If it's a multiple choice question, we're going to be done pretty quickly. Time, displacement, final velocity. All right, 0, 0, 0, 1, 2, 3, 4, 5, 6. Right? How far down? 5, 20, 45, 80, 125, 180. How fast? 10, 20, 30, 40, 50, 60. All right. Dropped from rest to reach the bottom of a 125 meter cliff to go 125 meters. All right, is going to take how long? How much time? 5 seconds. The answer is 5 seconds. We already know that the answer is supposed to be 5 seconds. So if it's a multiple choice question, we're done. All right, now, if it's a written question, we've got to show the work. So here we go. All right, what were we given? Well, how long? So they want to know the time. Right? The mass of the marble, I'm sure we don't need. I'm going to cross that out right away. I don't think we're going to need the mass of the marble. All right, this is a free fall problem. From rest, V initial is 0 meters per second. The distance it's going to fall is 125 meters. The one final thing you're going to have to put down as a given. The fact that the object is falling, it's in free fall, it's definitely being acted upon by the acceleration due to gravity, g, which is a type of acceleration. So 10 meters per second squared. All right, now, as far as picking an equation, we have an equation d equals VIT plus 1/2 AT squared. All right, so let's take a look. D, right? VIT is what we're trying to find, and 1/2 A right there. So we have everything except for the time. And since V initial is 0, this whole VIT is going to drop out. All right, if V initial is 0, 0 times this time, whatever it is still going to be 0. All right, now, D equals 1/2 AT squared. We're trying to find the time, so we need to get the time by itself. Let's multiply both sides by 2. All right, 2 on bottom, 2 on top. 2D equals AT squared. We're trying to get the time by itself. Divide by A on both sides. Cross that out. Flip it around. T squared equals 2D over A. I don't want T squared. I want T. Take the square root of both sides. And we're going to get T equals the square root of 2D over A. So I'm going to copy that equation. That's the version of this equation that we're going to be using because we're trying to find T. So T equals the square root of 2D over A. All right, let's do this. All right. Now, the distance was 125 meters. The acceleration, 10 meters per second squared. 2 times 125 is 250 divided by 10 is 25. Take the square root of 25. The time is 5 seconds. But we knew that from the magic chart. All right, but the answer is that the time, how long it takes, it's going to take 5 seconds for that marble to hit the ground from a height of 125 meters. Problem number 3. We have a 5-kilogram bowling ball dropped from rest. It takes 3 seconds to hit the ground. What height was it dropped from? We're on Earth. The object is dropped from rest. We can use the magic chart. All right, time, distance, VFinal. Whoop. 1, 2, 3, 4, 5, 6, 5, 20, 45, 80, 125, 180. Okay. It takes 3 seconds to hit the ground. It was dropped from a height of 45 meters. 3 seconds, it goes 45 meters. We already know the answer is 45 meters, but this is a written question, so we have to show all the work or we get nothing. Now, I want to emphasize, again, what showing all of the work involves. You list the givens. Here we go. All right, a 5-kilogram bowling ball. The mass of the bowling ball is 5 kilograms. I don't think we're going to need that. Dropped from rest, so V initial is 0. You might as well put down right away that the acceleration is 10 meters per second squared. All right, takes 3 seconds to hit the ground. The time is 3 seconds. And from what height? So distance is what we're trying to find. Okay? Got d VIT, 1/2 AT squared. Looks like this equation is going to work. Okay? We've got all those things except for one. When you pick an equation, You want to make sure you have everything except for one letter. Only one letter can be missing. Only one. The only thing that's missing here is D. And this is going to drop out because V initial is 0. All right, so D is going to be 1/2 AT squared. All right, so D equals 1/2. A is 10 meters per second squared. The time is 3 seconds. 3 seconds squared. All right, half of 10 is 5. 3 squared is 9. 5 times 9 is 45 meters. The bowling ball was dropped from a height of 45 meters, but we knew that. We knew that from the magic chart, so we know that our math here is correct. Let's do another problem. This problem is a little bit unusual. We're trying to just use a different equation. You'll probably never see a problem quite like this, but it's simple and straightforward. There's nothing difficult about it. You know, you're just going to be picking a different equation to solve it. Okay, so now a 62.3 gram pebble is dropped from rest. All right, so we know it's on Earth. We know it's dropped from rest. You can probably use the magic chart. All right, so let's see. All right, it's dropped from rest from the top of a tall building. At one point, the speed is 20 meters per second. It's going down. It's going down the whole time, obviously. At one point, the speed is 20 meters per second. At a later time, its speed is 40 meters per second. Now, we know that those are two speeds on the magic chart. So we can probably use the magic chart. What do they want to know? How far does it fall during this interval between the 20 meters per second and the 40 meters per second? All right, how far does the pebble fall? All right, so magic chart. All right, now I don't know for certain that we can always use the magic chart. Let's see if the magic chart helps us with this problem. All right, 0, 0, 0. Okay, time is 1, 2, 3, 4, 5, 6. All right, the distances are 5, 20. You got to memorize these guys, okay? You got to memorize these. You want to have some sense of how far things fall, how long it takes them to fall, all right, and how fast they're going, okay? 10, 20, 30, 40, 50, 60. All right, so from the point where the object is falling at a speed of 20, that's from here to the point where it's falling at a speed of 40 to here, how far does it fall during this interval? Well, it goes from 20 to 80. So it has fallen 60 meters during this interval. The answer should be 60 meters. All right, so let's show the work. If it's a multiple choice question, you're done. All right, let's show the work now. All right, remember I said the reason I picked this question is that I'd like to use a different equation that we haven't used yet. All right, so given. All right, we've got the mass of the pebble, 62.3 grams, dropped from rest. Well, V initial is 0, but we're really not focused on what happens from V initial. We're focused from 20 to 40. All right, so let's call, we're not starting here. The problem is really starting at 20. So let's say V initial is 20. All right, and V final is 40. All right, what we're focused on happened between 20 and 40. All right, now, we know it's falling, so A, which is G, is 10 meters per second squared. Anytime something is, okay, how far, D equals how many meters? Okay, now, picking an equation. There's an equation on the mechanics page. V final squared equals V initial squared plus 2AD. All right, so copy that equation. V final squared equals V initial squared plus 2AD. We're trying to find the distance. So we got to get that D by itself. So let's subtract V initial squared from both sides. All right, V final squared minus V initial squared equals 2AD. Trying to get D by itself, get rid of the 2A. All right, divide both sides there. That cancels. The equation we will be using, D equals V final squared minus V initial squared all over 2A. That's the equation that we want to be using. So let's put that equation up here. All right, D equals V final squared minus V initial squared all over 2A. Okay? All right, here we go. All right, V final is 40. All right, so 40 meters per second. That whole thing gets squared. Guys, watch how I plug in. You can't put the unit on the outside. You can't put the squared on the inside of the parentheses. The unit has to be inside the parentheses. The squared has to be outside the parentheses. Do it any other way, it's wrong. It's going to be marked wrong. You're going to lose probably all of your points. V initial, 20 meters per second. That whole thing gets squared. 2 times A, 10 meters per second squared. So what we've got, 40 squared is 1,600. All right? 1,600 minus 20 squared is 400. So we've got 1,200 divided by 20. Okay, and that's 60. Okay. Didn't we say it was 60 meters? All right. 1,600 minus 400 is 1,200. 1,200 on top divided by 20 is 60. All right, so yes, the magic chart said it was 60 meters, and our math says that the answer is 60 meters. Okay. One more problem, and I think you're good with the introduction to free fall. Last problem, and it's going to be a little bit different. A 200-gram baseball is thrown straight down from the top of a tall building with an initial velocity of 8 meters per second. All right, so what's different here is that the baseball, I have an apple, the baseball is not being just dropped from rest. We're not just letting it go. This person is throwing it down, right? Giving it an initial velocity that is not zero. So technically, the magic chart does not apply. Right? But what we can do is figure out how high the building would be if the baseball was dropped from rest. So let's try that just really quickly. TD V final. All right, so 0, 0, 0, 1, 2, 3 is about all we need. Okay, now, if it took 2 seconds to hit the ground and the baseball was dropped from rest, the building would be 20 meters high. But we gave it an initial velocity. We gave it a head start. We made it go faster at the beginning. So do you think that the distance it covers in that 2 seconds is going to be more than 20 or less than 20? What do you think? I'll let you think about that for a minute. Now, we gave it some extra velocity. We gave it a head start, so to speak. Right? If it was dropped from 0 with nothing, in 2 seconds of falling, it would have covered 20 meters. The building would have been 20 meters high. But we gave it a little extra push, a little extra velocity at the beginning. So do you think the building is higher than 20 meters or lower than 20 meters? All right, I predict that the building is higher than 20 meters. We gave it extra speed at the beginning, so it covered a lot more distance in those 2 seconds. All right, so now let's do the calculation. My prediction is that the building is more than 20 meters high. All right, here we go. Given. Now, we've got the mass of the baseball, 200 grams, thrown straight down. All right, so the initial velocity is 8 meters per second. All right, now, thrown down, negative 8 meters per second. All right, now the height of the building, all right, would be, well, the ball's going down. We're doing it from the perspective of how far down the ball travels. All right, so that would come out negative also. If it takes 2 seconds, the time is 2 seconds. All right, and the acceleration is g, which is negative 10 meters per second squared. What I want you to look at is that the initial velocity is negative, you're throwing it down. The acceleration is negative, the Earth is pulling it down. The displacement is negative. The ball is going from 0 up here, down. Since everything is negative, we don't have to worry about it. If everything is negative, then we don't have to put the negatives into the equation. All right, now, let's pick an equation. All right, I know the mass probably doesn't matter. All right, so the equation that I'm going to pick, d equals VIT plus 1/2 a t squared. We've got everything but the d. All right, so d equals v initial t plus 1/2 a t squared. All right, now, v initial is 8 meters per second. The time is 2 seconds. Remember, our prediction is the answer is going to be greater than 20. If the answer isn't greater than 20, I made some kind of a mistake. All right, so half 10 meters per second squared in 2 seconds. Square that. Okay, so 8 times 2 is 16, plus half of 10 is 5. 2 squared is 4. 5 times 4 is 20. Okay, so the height of the building, all right, the distance, the height of the building is 36 meters. Okay, so yes, the building is greater than 20 meters. Our prediction was correct. All right, now, just a quick little recap about free fall. What did we learn? What were some of the most important things that we learned in this video lesson? All right, just a quick little recap about free fall. So free fall is when an object is flying through the air. The object cannot have power of its own. No engine, no wings, right, nothing to cause it to change its motion on its own. Now, the only force that can be acting on that object is the gravitational force of the Earth pulling the object straight down. Now, it doesn't matter. Let's take a baseball, okay? It doesn't matter if you just drop the baseball, all right? So the baseball is going down, all right? It doesn't matter if you throw the baseball straight that way, all right? Actually, let's not draw that. If you throw the baseball that way, it's going to go down like that, all right? You can take, for example, if you take a football, all right? Take the football and throw the football in an arc, all right? There's your arc. I'll put the football here, and then the football is here. Okay, the bottom line is that the whole time the baseball is falling down, the Earth is pulling it straight down. The whole time the baseball is going this way, all right? The whole time the baseball is going this way, the Earth is pulling it straight down. The whole time the football is going across, the Earth is pulling it straight down. Now, today with this lesson, we only looked at this type of a problem, where the ball, the marble, the bowling ball, whatever it was dropped straight down. All right, when we look at free fall in future videos, the balls will be doing other things. But once you let that ball go, the definition is the ball is in free fall. The only force on the ball is the Earth's gravitational force pulling it, the object, straight down. All right? So do some easy free fall problems now. We will do some more difficult free fall problems in later videos.